Welcome back to our December iteration of our Innovate seminar series in collaboration with the University of Santa Barbara, California, Santa Barbara, with their Kavli Institute for Theoretical Physics, KITP. And so if you've been following this series, you've seen a host of amazing talks and amazing research being highlighted by our NSBP members. My name is Elon Price. I'm your host for today, and I am the student representative for the National Society of Black Physicists. And today I'm super happy to open the session and introduce our speaker, Alan Pierre-Louis. Alan is a fellow student council member, and he is also a student chapter president. But what I can say personally about Alan is that he's always brought good vibes, good energy, and among everything else, just like with the rest of our student council members, he has been a dedicated leader. And so I would like to dive a little bit deeper into Alan to give you some context to who he is. He also has been a GEM fellow, or currently a GEM fellow, an Edward Bouchet fellow, and he is a staff researcher at Brookhaven National Laboratory in the Center for Frontiers in Nuclear Science. He's a master's student at Stony Brook University, where he, as I said, is the president of Stony Brook University NSBP student chapter. And he will be going on soon to join us in the good fight for trying to get our PhDs. Specifically diving into his research, he's going to be talking about his feasibility studies for the soon-to-be-built Electron-Ion Collider at Brookhaven National Lab. And he specifically looks at the constructions of cosmic ray trackers and gas electron multipliers. I won't get too much more into the science. I'll leave that for Alan. But at this time, I'd like to turn it over to Alan for his seminar. Thank you so much for being here.
Thanks for the intro, Elon. Let me make sure everyone can hear me, and I'm going to share my screen. Talk is going to be on the feasibility of elastic electron-proton cross-section measurements at high Q squared. So I'll explain what all these terms mean. So the first section of the talk will be talking a lot about the Electron-Ion Collider that's going to be built and some of the statistics that we can use to probe physics at a higher level. And then I have a small section on the molar experiment, which is at Jefferson Lab, and that's where some of the other hardware aspects come in that Elon talked about. So I'd just like to acknowledge my collaborators, my PI, Professor Deshpande, my collaborator, Brock Schmuckler, amongst others, and Stony Brook University and Brookhaven National Lab, as well as the GEM Fellowship for kind of helping this research along. So to give context behind what exactly the big picture is here, is that the EIC, or Electron-Ion Collider, is going to be built on top of RHIC, or the Relativistic Heavy Ion Collider. So when we say colliders, imagine these huge underground tunnels, that's what they are, and then they accelerate particles to near the speed of light. And then these particles hit each other. When they hit, we actually get information about physics. So either there's some breakup that happens, or particles can bounce off of each other. Detectors then detect where they go and what's happening, and we can interpret and analyze that data. So for example, proton behavior can be examined after one of these collisions, and we can gain insights on form factors. And then form factors, for example, can help us understand charge and current distribution, which becomes important in physics, as we all know, for electricity and magnetism. So in this study, I'm going to show how we can isolate elastic collisions, or collisions where one particle just bounces off the other after their collision. I'll show how we can statistically isolate those, so then we can study them for the Electron-Ion Collider that's going to be built. So here we have the generator level. So the generator level, what I mean by that is that there are computer programs that help simulate millions of events. And what I mean by events is that it's simulating this electron-proton collision. Those are the two particles in consideration for today, an electron and a proton. So one's negatively charged and one's positively charged. And then Pythia is a simulation package that gives very fast approximations of what's happening when those collisions occur. So we have a bunch of events, 100 inverse femtobarns worth of events to be exact. So that's just a number of events happening. And then it's over the q squared or square of transferred form momentum range. So we are going from about 5 GeV squared to 40 GeV squared. That's our energy range. So to the right, we have q squared, or this energy threshold from 0 to 40, but we're really considering more 5 to 40. And then that's against events per GeV squared per the 100 inverse femtobarns. So basically what this is saying is that we have a lot of events. We have from 5 to 40, we see that there's plentiful data points that we can grasp from to do this study. So we're confirming that these events exist so that we can actually statistically research them. Underneath that are two plots of the energy regime of the q squared versus eta, or an angle. So the angle of the proton and angle of electron. And as we can see from there, similarly, we have a lot of data that we can draw from there. So that's important because we need to figure out if we're actually observing anything to begin with, right? Reconstruction happens when we need to reconstruct kinematics. So the kinematics of these collisions basically refers to the mechanics and things that are happening on that level when these two particles collide. And it's necessary to reconstruct because these are simulations, and there are occasions where we have dilemmas. So to be clear, the scattered electron method is the typical method of kinematic reconstruction. What that means is that after the proton and electron hit each other, the typical method is that we look at that scattered electron and get information from that to see what was happening physically. However, sometimes that the electron is not detected for whatever reason, or the reconstruction just comes out poor. So we have to have different methods. So there's 3 different methods of reconstructing these kinematics. So the scattered electron method, like we just mentioned, the Jacquet-Blondel method, which only uses hadronic information. So in the case of Jacquet-Blondel, same story, you have electron versus proton, they hit, but you're only going to take the data from the proton at that point. So that's what we mean by only hadronic information. And then double angle, and double angle takes info from both the electron and the proton. So those are our methods of reconstruction. And then we're going to plot that against q squared, or the energy regime that we mentioned. So the true q squared versus this reconstructed q squared. And this is a nice schematic here that kind of shows what's happening. So towards the top, you can see that there is some sort of proton beam going directly against an electron beam. And then these eta ranges are the angles, right? So this is representing a detector. Our study went from negative 3.5, so somewhere in this regime, all the way to positive 3.5, so somewhere in this regime. So that's what this is showing. So for reconstruction, there are some equations that can be seen here. So towards the top one, we have Y, that is the inelasticity. So that's the fraction of electron energy that's lost in the proton rest frame. Q squared is what we mentioned before. So that is the transferred form momentum. So here it's representing the energy regimes that we want. And then MP would be proton mass, and X is Bjorken scaling. So that's like a scaling factor for our particles. In an elastic collision where one particle hits another and they just bounce off, the Bjorken scaling X is just 1. So for each of these, we have 3 plots. The first one is the Jacquet-Blondel method, and we see that's pretty poor. There's not a lot of agreement between the y-axis, which is the q squared for the Jacquet-Blondel method, and the true Q squared, which we had before. For the scattered electron method in the middle, it's better. We see that there's more agreement there. But for the double angle, we see that we have a nice clean plot. So this is what we're seeing, that the double angle method, or the method that takes into consideration both the electron information and proton information after they've collided, that is what's giving the best agreement here. And then for the X, or the Bjorken scaling versus the true Q squared, we see that the double angle is the only one that has a good plot. So it's important that to use the final electron and final proton information here. So another aspect of this statistical analysis that we're doing is that in order to study what we want to study, and in this case it is elastic collisions, we need to be able to get rid of backgrounds. And that's important because within these collisions that are happening at the Electron-Ion Collider, when it's built, we won't only have situations where there's an electron and proton hitting and they just cleanly bounce off each other. There are times where you have inelastic collisions. And the inelastic collisions represents processes where there's some sort of breakup. The proton can decay into other end products, and at the end of the collision, you don't just have the electron you started with and the proton you started with, but instead you have other species of particle or decay product that is there, and that's what we want to avoid. So in order to actually study what's going on, we need to do cuts or vetoes. So what's happening in that situation is that we use statistical methods to make sure that we're isolating our events, so we only have elastic events. Only events where an electron and proton directly hit each other and bounce off, those are the only ones that we want to consider. So in order to do that and confirm that, we have to confirm that we're out of the range of particles being produced like pions. And we have to statistically determine that we are not observing inelastic electrons, so electrons that are forming in cases that are not elastic. So there's some sophisticated statistics that we go through, and I'll break it down. So there are these vetoes, and basically they are criterion that the data has to go through, and if it doesn't match this, then it gets discarded, so that we're just dealing with what we want. So the events have to contain only two particles, which are the scattered electron and a proton. If there's some other particle, we know that that's not an elastic collision, that was some inelastic collision, and there was some breakup. So if there's any more than two particles, that's the first cut. So anything of that sort is eliminated. The electron and proton have to be coplanar, so in the phi angle, they have to be on the same plane, meaning they're hitting directly head on. The electron and proton transverse momenta have to balance, meaning that they're equal in their momentum. And then you have to confirm the total energy of the proton and electron after they've hit, and you have to determine the total z component of their momentum. So what we can see here is that after generating 100 million events, for both the case of the Q squared, or the energy regime being over 0.5 GeV squared and over 3 GeV squared, we see that these statistical cuts make it so that after each successive veto, we eliminate any events that don't match our criterion. So that's what this plot is illustrating here as well. So to go further in depth as to what's happening, here is an example of yield plots. So it's yield versus eta ranges. Eta is in the top right corner of each of these plots. So that's angle. And what we can see here is that the elastic electron range, or the range of the electrons that we want to observe, which are electrons that have been hit by the proton and then just scatter off, it seems that from our statistics that this red line is always outside of the yield for the blue here. And the blue represents negative pions. Negative pions could be confused for the electrons, but we see that statistically here, the elastic electron range is always outside of the negative pion range. So they don't overlap, meaning that statistically we can rule out the negative pions. Similarly, we have this blue range and this green range, green being the positive kaons, and then blue being positive pions, and the red represents the elastic proton range. So we see here that this red line is always outside of the overlap of the pions and kaons. So this green and blue plot is always just missing the red line. So we know that the range of the elastic protons is always out of range of the pions and kaons. So we can statistically rule those out as well. It means that we don't see any overlap. There is a problem though when we have electrons forming. So there are decay electrons that can form. So the thing about them though is that they come with decay positrons. So we will see in a minute when we get to the plot that the decay positrons are generated always with the decay electrons. So that realization allows us to statistically cut out the positrons, and then we'll be cutting out the decay electrons that are produced with them at the same time. So all the unwanted products that we're getting, so anything that is not just a proton and electron hitting each other and bouncing off, everything of that sort is covered and not considered in the study. So we're eliminating tons of statistical background here. So as you can see here towards the right, the decay positrons are highlighted in pink and the decay electrons are highlighted in black. Now, what's important to note here is that they are being produced directly on top of each other. So when they're being produced directly on top of each other, we can know that each decay positron has an associated decay electron. And from there, you can statistically cut it. Once you look at the left, applying all these different vetoes for 500 million events, it also shows that we're eliminating these unwanted products from our consideration. So what we're showing here is that we definitely are able to observe just the electrons and protons in the elastic case, which is what we want to study for the Electron-Ion Collider. So for the future, we've published these results already on ArcSci, and we've done these types of statistical experiments also in the limit of 18 GeV electrons on 275 GeV protons. The problem with this, though, is that when we do the same things for these energy regimes, we find that we don't get anything in the graphs, so the graphs all appear empty. And basically what we're seeing is that at such a high beam setting, these events are like a completely different area of our phase space, and there needs to be more studies to actually adjust things so that we can actually see anything in those regimes. So we can't use the same methods. But it's helpful to know that at this higher energy regime, we can't see anything, but from what we got, which was the 5 GeV electrons on 40 to about 41 GeV protons, which is the highest energies to date for colliders of this sort, we were able to statistically prove that we will see something. So simulation has shown that this will be something reliable to look for at the Electron-Ion Collider once it's built. So yeah, that concludes the talk on the side of the EIC, and I just wanted to give a little bit more detail on some of my current work. So at the suggestion of my advisor, so there's something that's going to be called the molar experiment, and the molar experiment is at Jefferson National Lab. You can see towards the right. This is a demonstration of the detector array, some toroids, and a target and electron beam. So molar stands for measurement of a lepton-lepton electroweak reaction. So you might be asking, what is molar and what is the physics behind it? So this is a different experiment that's not at Brookhaven National Lab, but is at Jefferson National Lab in Virginia. So basically what it wants to probe is molar scattering. So it's funny because the acronym is the same as the name of the scattering that's named after a scientist named Molar. But basically electron-electron scattering is also known as molar scattering. And electroweak theory suggests that there's a connection between the weak force in physics and the electromagnetic force. So the goal of molar is to measure some rapid reversal of an electron's helicity. And then when you measure the asymmetry there and the weak charge that's yielded at certain precise angles, we should be able to compare that to theory. So if there is any result there that does not match theory, then we would have landed on some new physics beyond the standard model. So this is high precision physics. The last for the EIC, the last thing I showed you was high energy physics, high energy nuclear. So it's at the highest energies to date, but this experiment is the highest precision to date. So this would outclass SLAC's E158 experiment that did something similar. So in terms of what I have helped with at Stony Brook University is that I've helped with the fabrication of prototypes for gas electron multipliers. So what these are detectors. In order to measure the electrons that are being considered in this case of electron scattering, you actually need to track the angles and the ranges of the electrons that have actually scattered, correct? So this is more of a hardware project, whereas in my previous work, I was doing simulation. So the gas electron multipliers, to clear up how they work, is that they are sort of like a flat plane, and there will be pictures later, but basically they work by, they first intercept the electrons, and there's a gas that is interspersed inside, and then the incident electron causes a gas avalanche and electron multiplication, and these electrons travel through small holes on the micrometer scale, and they're etched in a foil. Basically, the rapid movement of these electrons causes a signal on the nanosecond time scale, and basically the data is read out by these digitizer cards. So there's different electronic hardware that can pick up on when these electrons are moving, and then go through various computer systems that then connect to your whatever final system you have, so then you can analyze the data. And then this tells us about information about the angles and everything that the electrons were doing once they've scattered. So I'm showing here some of the processes in making these gas electron multipliers. So making of detectors is quite arduous, but there's the first picture is showing the foil that we mentioned, and the foil is apical polyimide. Sometimes you'll see it referred to as Kapton, but to be specific, this is actually a apical polyimide. So we have to cut that. Then we press the foil down onto our boards that we get. And then the third picture is showing after everything's been pressed and glued, there needs to be air leak testing, or making sure that our gas lines are all secure so that the gas that's actually inside of these detectors doesn't leak out, so then we can have our nice electron avalanche. And these detectors, as you can guess, are very sensitive. So sensitivity to electrons means that we're also probably going to pick up cosmic rays. Cosmic rays are coming through and piercing Earth's atmosphere all the time. At our elevation of like human basements or buildings, ground level, what we're going to see is that most of the time we're encountering particles called muons. So in order to test the sensitivity of the detectors to the particles called muons, you have to make a cosmic ray tracker. So a collaborator and I built the frame for this. So this whole like the casing that these stand on and the beddings wrapped in plastic, we made that together. But for myself, I was able to secure scintillators. So the scintillators are in black here. I was able to hook up and like put together these tubes and make the rest of the actual tracker. So what happens here is that for each of the PMTs labeled, we have a scintillator, and the scintillator is this flat pad of some sort of plastic. Once a muon or a cosmic ray comes through, and they're coming through all the time, every second, um, these scintillators react and create some sort of excitation within themselves. That excitation is then amplified electrically by diodes, which are inside of a PMT, which is this tube here. So the PMT stands for photomultiplier tube. From there, we are able to hook these up to a logic discriminator and a logic gate and discriminator, which basically interprets the pulse from the PMT, and then it goes to a trigger that then alerts our computer, and we can then interpret data that we get from the setup. So we have 3 PMTs here. The reason that we have 3 is that you want to ensure that when you have some muon or cosmic ray coming through, that we know that this is not just a coincidence or a fluke, but they're all getting hit at the same time. And if they're hit at the same time, then that means that we have found a cosmic ray or muon. So that's what we're considering here. And you put the gem in between them so that the gem is also connected to the computer systems, and we can interpret data on that end as well. So for future work, the cosmic ray tracker will help in testing sensitivity for these gems. I'll be working on hardware and interfaces for data acquisition. We were able to do a little bit with the cosmic ray tracker in helping test sensitivity for the gem prototypes and micro R wells, which are another type of detector. And the team at Stony Brook here was able to go to CERN and kind of further test these. So I was happy that the cosmic ray tracker was able to help a little bit in that regard. And the gems that we construct after we make these prototypes, they'll be mounted in the molar experiments to aid in the detection of electrons. So basically, the first thing that I went through was the Electron-Ion Collider and how I did simulation research there. And now I've just gone through some hardware for the molar experiment. So I'll be happy to take any questions. And thanks so much for inviting me to give this talk.
Thank you so much for the wonderful talk, Alan. I just want to remind all of our attendees that you can leave any questions you have for Alan in the Q&A panel below. Yeah.
Yeah, maybe I'll go back and share a screen again. Oh wait, let me see this question that just came in.
So there's a question by Majir Farzad, and he is asking if you could say again what reconstruction means. And he says you gave a great talk.
Okay, thanks, Mazir. So reconstruction just means that the kinematics that are under consideration have to be shown again. So this is a simulation, but for example, when you have an electron versus a proton, you can't rely just on one method of showing that these scattered off each other. Because sometimes in a real experiment, you will not be able to detect the electrons. There's always some sort of problem that could happen with detectors, or simply you could have a bad plot of the kinematics under consideration, right? So in order to kind of go around this, you have multiple methods of reconstructing. So what it means is that you're taking your simulation data and plotting different aspects uh, of the mechanics of the situation or the kinematics. So, from what I showed, it was Q squared, or the energies versus one another. So that becomes important in showing if you're doing things correctly or not.
Thank you. We have another question in the Q&A panel that asks, Paul Sorensen asks, how many cosmic ray muons did your detector see, and was it enough to characterize the GEMS?
Yeah, so there is a counter. So the counter is connected to our computer system. So whenever we have a coincidence of muons flying through the atmosphere and then hitting all three of the scintillators, or the scintillators used in the cosmic ray tracker, that's when we get a count. So on the order of a day, going through a day, we're going to get hundreds, and then those hundreds will then typically we'll get like on the scale of hundreds. And in terms of characterizing the gem, we're working on that. Unfortunately, there was not a lot of time between the time that I had made it and then the time that the CERN team wanted to use it, but they were able to get some results. So they were able to characterize, but they to be careful and to just get more savory results that are less rushed. They're back now, and we're making more gem prototypes, and we have micro R wells that might need actually a smaller active area for all of our scintillators, which is something that we're thinking about, but I don't think that we have anything smaller right now. But it should be enough. We are getting cosmic ray data and we can analyze it, and it should be enough for the gems. I think our team is just focused a lot more right now on making the gem prototypes.
Thank you. Oh, we have another question in the Q&A panel. Latoya Anderson asks, for the Electron Collider, what is the proton source, and do or would the number of successful collisions vary based on that source?
Really good question. I actually don't know what the source of the protons would be. Typically, I know like with sources that they use some So the method that they use for sources is pretty interesting. I am actually not sure what they're using for the proton source. In terms of the second part of the question, where it mentions the number of successful collisions vary based on the source, I'd imagine that there would have to be some variance there. But it's a great question. I'm not actually sure what they're using for the source. It hasn't been built yet, but probably that's something that would be definitely be on like the technical design report or the yellow paper for sure. But yeah, it's a good question. I think that a lot of what we're doing in the study is fast approximations. So if I had used a program called JAUNT4 would actually require that, like, it's almost like CAD for mechanical engineers. So you actually have to design the detectors and like put in the values and everything. Whereas this is more of fast approximations in a simulation that show that what we're doing is possible or feasible. Whereas with JAUNTs, if somebody did a simulation with that, that's more detailed, a lot slower, but probably they would know more about. They would have to factor in what the actual source of the protons are. But it's a good question though. What I did here was more use fast simulation packages.
Thank you. I think we're entering our final call for questions. So just a reminder, if you have any questions, you can leave it in the Q&A section.
I have a more general question if I could hog the Q&A for a second. I'm kind of curious what led to your interest in this research and like what you see for your future career goals. Do you want to continue this type of research or do you have a goal in mind?
Which experiment? Just
The
both?
one that you primarily built, I guess the molar experiment.
Okay, so in building the cosmic ray tracker for the Muller experiment, and I guess I'll answer both actually, but for that side of things, that was definitely a lot more along the lines of the team needed it, and then I was able to build it from reading on my own. So um, it became really interesting to me because uh, I really like particle physics and I like nuclear physics. And within other fields of physics, if it has any sort of particle stuff, then I just get really interested. So I guess like I will be guilty and say that a lot of if I'm interested in something, then I can do it like super fast. So I was able to kind of like put together the cosmic ray tracker in like less than 2 weeks. But for something along the lines of the gem detectors, it is a lot more involved and it is detecting electrons, but it is something that is a lot more of a team effort. And so I would say that I helped there, but I was definitely more involved on the tracker side. And from there, now I'm kind of helping with hardware surrounding the tracker and surrounding the other experiments in terms of like their computer interfaces. For the electron-ion collider research, that was more me just kind of. So I've been with the same group, the Deshpande group, since 2019, and I was just super interested in QCD, so quantum chromodynamics, and how the world works at the smallest scales. So we still don't really know a lot about quarks, gluons, all these things. So the electron-ion collider, in addition to just collision research, um, they often talk about these electrons when they're hitting protons or hitting other things. The electron-ion collider is called like a CT scan for particles. So we're going to learn more about the tomography or like what actually the quarks and gluons actually look like. at the level of, they're the quark and gluon level, which is super exciting for me. Like the fact that we still don't really know exactly how that looks is surprising to me, because in the same way that, like the atom symbol is like this like little circle with all these rings surrounding it, that's the Bohr model, but we know that that's not true, right? At the level of quarks and gluons, where you need an actual picture of like what to draw, like how are the quarks and gluons attached to each other, that's still an open question, which is like, okay, that's very interesting. That is still an open question. So that's kind of like where it comes down for me. That's what I was interested in. And for the future, anything that's involved with particle physics, nuclear or high energy is definitely for me. I've been like bugging a lot of the theorists around me about like quark gluon plasma and like hydrodynamics and magnetoacoustic waves. I've just been like asking them a bunch of questions. So anything regarding like plasma, which is different. There's different types of plasma. So quark gluon plasma, and then laser plasma acceleration, which is a whole different story that's going to help improve colliders. So those two different types of plasma, and then anything in the high energy nuclear and particle regime, all those things like are super interesting to me.
Thanks for that, and best of luck. I am very, very confident in your abilities, having to get to work with you, and I really appreciate you sharing your research today. And thank you to all of our attendees for listening, and all of the people that are here watching the recording. We are right on time, so we're right at the end of our session. And thanks again for joining. And that's all we had for you today. Stay tuned for our next Innovate seminar speaker.
Thanks so much.